Now I'm going to discuss verification by model checking. In verification by model checking, under model checking syntax tools properties, I will discuss mutual exclusion and NU SMV model checker. Under branching time logic, I will discuss syntax of CTL, semantics of computation tree logic. Under CTL and tree expressive power of LTL and CTL, I will discuss LTL and CTL as subset of CTL. So, my first topic is mutual exclusion. In this topic, I will be explain the function of the mutual exclusion. So, when concurrent process share a resource such as a file on a disk or database entry, it may be necessary to ensure that they do not have access to it at the same time. Several processes simultaneously editing the same file would not be desirable. We therefore identify certain critical sections of each process code and arrange that only one process can be in its critical section at a time. The critical section should include all the access to the shared resource. The problem we are faced with is to find a protocol of determining which process is allowed to enter its critical section at which time. Once we have found one which we think works, we verify our solution by checking that it has some expected properties such as the following ones. So here safety and liveness, two properties. In safety, only one process is in its critical section at any time, and liveness, whenever any process requests to enter its critical section, it will eventually be permitted to do so. Non-blocking, a process can always request to enter its critical section. Now, no sticking sequence is the process need not enter their critical section in strict sequence. So, come on the diagram, the first attempt model for mutual exclusion. Here, we explain the two processes, each of which is its non-critical state and or trying to enter its critical section T or its critical section C. Each individual process undergoes transition in the cycle and imply of T, T imply of C and C imply of and so on. But the two processes interleave with each other. Consider the protocol given by the transition system M in given the figure. So here G, legacy of the C1, conjunction of C2, G, T1 belongs to F C1. Now, the figure here in this figure show the second attempt model for mutual exclusion. There are two type state representing by T1 and T2. So, move to its trying state, but only one of them can ever make in transition at the time. It is called asynchronous interleaving. At each step, an scheduler determines which process may run. So there is a transition arrow from S0 to S1 and S5. From S1, again two things can happen. Either process 1 move again, or process 2 move. Here, for example, process 1 cannot move into S7 since it cannot go into its critical section until process 2 comes out of its critical section. We would like to check the four properties by first describing them as temporal logic formulas. So, here again the condition is the new symbolic model verifier. It comes NU SMV model checkers and check the validity of LTL. The NU SMV stand for new symbolic model verified. NU SMV is an open source product, is actively supported and has a substantial user community. For NSCMV, sometimes called simply SMV, provide a language for describe the models we have been drawing as diagram, and it directly check the validity of LTL formulas on those models. SMV takes as the input a text consisting of a program describing a model and some specification. It produces as output either the word true if the specification hold, या trace showing why the specification is false for the model represented by our program. SMV program consists of one or more modules. See, the code is showing the function of the NU SMV model. In that, the expression can be non-deterministic. Non-deterministic is used to model the environment and for abstraction. It consists of program and specification. The program has two variables, request of type boolean and status of enumeration type ready or busy. So 0 denotes false and 1 represents true. The initial and subsequent values of variable request are not determined within this program. This conservatively model that these values are determined by an external environment. The under specification of request implies that the value of variable status is partially determined. Initially it is ready and it becomes busy whenever request is true. If request is false, the next value of status is not determined. So here also the program therefore denotes the transition system shown this figure. There are 4 states, each one corresponding to a possible values of the 2 binary values. Note that here busy as a shorthand for status is equal to busy and request for request is true. The program and the transition system are not non-deterministic as that the next state is not uniquely defined. To check whether there exists a path from S satisfying the LTL formula, we check whether all paths satisfy negation of the psi. Here the syntax of the CTL. So syntax of the computation tree logic, if psi is atomic stratification is determined by the L, if the top level connectivity of the psi, the satisfaction is given by the usual truth table definition and further equation down the psi. So the next topic is branching time logic. Branching time logic, the LTL formula are evaluated on path. We define that a state of a system satisfies an LTL formula if all paths from the given state satisfy it. Thus LTL implicitly quantities universally over the path. Therefore, properties which assert the existence of a path cannot be expressed in LTL. This problem can partly be alleviated by considering the negation of the properties in questions and interpreting the result accordingly. So here the definition of that. Now syntax of the CTL, which is already discussed here. Semantics of the computation tree logic. The computational tree logic, CTL, it's short form of the computation tree logic, is a branching time logic, meaning that its model of time is a tree-like structure in which the future is not determined. There are different paths in the future, any one of which might be the actual path the realized. So here we define the CTL formulas inductively with Baker's new form as done for LTL. So here if the loop level connective of psi, then satisfaction is given by the usual truth table definition and further recursion down the psi. If the top level connective is a operator beginning, then satisfaction holds if all paths from A satisfy the LTL formula resulting from the removing the A symbol. Next is if the top level connective begins with the E, then satisfaction holds if some path from A S satisfy the LTL formula resulting from removing the A. In LTL, all paths which have a P along them also have a Q along them by writing FP imply of FQ. The next point is in LTL, all paths which have a P along them also have a Q along them by writing FP belong to FQ, but not possible to write in CTL because of constant that every F has an associated A or E. AFP imply of AFQ means if all the paths have a P along them, then all paths have a Q along them. Here, CTL temporal connectivities is a pair of symbols. The first of the pair is one A and E, a symbol along all paths inevitably, and E means along at least one path. The second one of the pair is X, F, G or U, meaning next state of X, F for future state, G for all future states, and U for until. The pair of symbol in E, phi universal of the psi, is the example of the EU. Now the CTL pair of the symbol like EU are individual. Notice that AU and EU are binary. The symbol of X, F, G and U cannot occur without being preceded by an A or an E. Similarly, every A or E must have one X, F, G and U to accompany it. So, here the CTL formulas are interpreted over transition systems. Let M, S imply of L be such a model. S belong to S and phi are CTL formula. The definition of whether M, S exists of the psi or is recursive on the structure of phi and can be roughly understood as follows. So we already discussed the last three topics. Now the second one is describing the not possible to write this in CTL because of the constant that every F has a associated A or E. There A, F, P imply of AFQ means if all paths have a P along them, then all our paths have a along them. CTL star is a logic which combines the expressive power of LTL and CTL by dropping the CTL constant that every temporal operator like X, U, F, G, we already discussed the meaning of these letters, has to be associated with a unique path quantifier A and E. A for the every and E for the someone. Here the state formula which are evaluated in states, which is defined by psi is equal to T, P negation of the psi conjunction of the Q psi and A alpha of the E alpha. So the term is which is defined here, it's described the if it's possible to get the state where started hold but ready doesn't. For any state if a request occurs, then it will be eventually be acknowledgement. So now the formulas of the CTLs, it's the two CTL formulas phi and psi are said to be semantically equivalent if any state in any model which satisfies one of them also satisfies the other. We denote this by the phi belongs to of the psi. So path formula which are evaluated along path. This formula is described about the all the CTL's explicit quantification over the path. This diagram, it's a common diagram of the CTL star, which is a combination of the characteristic of the LTN and the CTLs. So although the syntax of LTL does not include A and E, the semantics viewpoint of LTL is that we consider all paths. Therefore, the LTL formula alpha is equivalent to the CTL star formula A alpha. Thus, LTL can be viewed as a subset of CTL star. CTL also a subset of CTL star since it is fragment of CTL star in which we restrict the form of path formula 2. So, in the diagram, the relationship among the expressive power of CTL, LTL and CTL star, the characteristics of the CTL, LTL is the combined in the CTL star. So the relationship among the expressive power of CTL, LTL and CTL. Here are some example of formula in which in each of the subset showing in the diagram. So here in the given diagram, the CTL starts showing the combination of the LTL and CTL that describe the proof of AGEF P is not expressible in LTL is as follow. Here phi be LTL formula such that A phi is allegedly equivalent to AGEPG since MS exists if AGEP P in the left hand diagram. Below we have M S exists A of phi. Now it M be show in the right hand diagram the path from the M are subset those from S in M. So we have M as exists of A phi, yet is not the case that M S belong to AGEF P is contradiction. So these are the explanation of the verification by model checking, in which we discuss the CTL, LTL and CTL virtual execution. So the end of here in the CTL star involves two classes of formulas, state formulas, and the second is the path formulas. So the next is now. Thank you for listening me. Good morning everyone, myself Himanand Kumar. I am doing m.tech from PS University under branch Computer Science Engineering. Today I am going to discuss about verification by model checking.